Hello, everyone. Welcome to our webinar about key benefits in the characterization of AFM-in-SEM in fields of powders, particles, and 2D materials. I am Veronika Hegrova from Application Department, and today I'd like to talk about, first of all, I'm gonna introduce AFM-in-SEM as a solution for advanced capabilities of SEM. Then I'd like to focus on challenges and needs for future technologies. And I'd like to focus on powders and particles and two-dimensional materials. So first I introduce the solution, and afterwards we're going to have a look at a few examples and explain the solution on use cases. Atomic force microscope, LiteScope, which is designed to be integrated into scanning electron microscope. So it's quite compact and it's fixed onto the stage, and otherwise it doesn't affect anything else in the SEM. And I'd like to start with the motivation. Why AFM in SEM? The reason is that these techniques are complementary, and if we are able to measure both AFM and SEM together in SEM chamber, we can get more information and understand the properties better. So, for instance, we can measure precise topography together with mechanical properties and have a look in SEM using backscattered electrons or EDS, etc. One of the main benefits, which I'd like to point out here, are in situ sample characterization, as we don't need to move and transfer the sample to other microscopes. The second of all is correlative multimodal sample analysis. As we have more instruments in one, we can measure more modalities together. And the third one I would point out is a precise localization to the region of interest. As SEM has wide field and very good resolution, we can navigate the probe and localize the structure we'd like to acquire. We are focused on samples and measurement of informations which are otherwise not possible to acquire, or the experiments are extremely complicated. We offer several modes. I would go just briefly. We measure mechanical properties such as elasticity, hardness of the material, electrical properties, for instance, conductivity mapping or surface potential measurement, magnetic domain imaging, something in between. We can measure piezoelectric domain imaging. And from the spectroscopy modes, we can do IV curves, force distance spectroscopy, or time spectroscopy, and we can correlate most of them together with with SEM capabilities. We focus on, I would say, 4 main areas: material science, nanostructures using focused ion beam gas injection system or whatever is in the SEM, semiconductors field for failure analysis, and life sciences. But why are we here today? I'd like to show you a unique characterization capabilities of AFM in SEM. And in order to understand the macroscopic properties of devices, we need to have a look at lower ranges. So we need to have a look at microscopic properties. It is important to know the sizes and shapes of compounds. And so for that reason, they are studied, and we try to understand better the material behavior. Most of the devices are composed of smaller particles. So if we are able to measure smaller particles, such as powders and particles or 2D materials, then we can measure or we can evaluate the macroscopic functionality of the device and improve it. And so in this way, if we are able to understand the properties on the micro and nanoscale, we can move forward the technology in the future in drug delivery of pharmaceutical industry or additive manufacturing, semiconductors, or batteries, and so on. And so the proper understanding and improvement of the smaller particles or the adhesion of particles into one compound can enable us to have lighter and stronger materials, enhance the performance and efficiency of the devices. Deep understanding is very important, for instance, in production of processes and functionalities of powders and particles in different fields. And if we understand it well, we can optimize the production. So AFM-in-SEM represents a unique solution. I like to focus today on determination of surface roughness of powders and particles, and in complex characterization of 2D materials properties, because understanding the material properties such as mechanical, electrical, or magnetic related to chemical compositions is fundamental for the development and use of functionalized 2D materials in practice. Let's have a look at powders and particles. Here I have a short recording how it can look like when we measure the topography of the particle or other properties. So we see the particle here and the very sharp tip on top of it. And why is it important to measure the powder-to-powder interactions? They are important in order to wide range of industrial processes. It's important in pharmaceutics, ceramics, paints, and coatings of metal components or catalysts. And we'd like to focus on the surface roughness as it directly influences some of the interactions. And so far, from our knowledge, no widely used method for surface roughness exists. So today we're going to focus on surface roughness of particles, but other properties such as magnetic or electrical properties can be analyzed as well. I'd like to show you an AFM-in-SEM, which offers unique capabilities to directly determine the surface roughness. We optimized the solution, we updated software functionalities, and I'd like to show it to you on two case studies. One is from pharmaceutical industry, and one is from ceramics engineering. But before we have a look at the use cases, I'd like to explain the measurement workflow. So first of all, we will localize the particle we'd like to acquire, and then navigate the tip. Further, we're going to measure the AFM topography along the shape of the particle, and then we will calculate the roughness by using the functions in the software. But how it looks like in reality, we have SEM overview here. From top view, we navigate to the particle, the probe. So in XY, we are on the particle, get exactly where we'd like to be. And then we need to get to the particle. So we are approaching here in the tilted view. We can see how we are getting closer. we are on the particle, and the last thing, we start measuring. This way we obtain the surface roughness, or we obtain the topography, and further we need to determine the roughness of the sample surface. We have the calculations built in the software. So first of all, we need to correct the background as it's a small particle. So we can choose polynomial or spherical fit, or there are others, in this case, not used. The second thing, we need to select area we calculated the roughness from. We have several different shapes we can use. And the last, we calculate the roughness. We choose the parameter. Afterwards, we can set several squares or areas of interest, and afterwards we export it. The last thing, how it looks like in the software. So first we choose a suitable fit, then measure the surface roughness from area we want. And we export it. So it is quite easy to do it directly in NanoView software. And so let's have a look at more interesting thing. And it's the application in pharmaceutical industry. So in order to understand, if you're not familiar with pharma, we're going to talk about and have a look at API. It is an active pharmaceutical ingredient which contains the key drug molecule. And these are pharmaceutical carriers, and they are here to provide drug delivery into our body. So we need to bind the API somewhere on the particle and then get it into our body, and then chemical reactions in order to get it where it's supposed to be. And so the understanding of API binding principles plays an important role in development of new targeted drugs delivery. So as we see here, the API in the red can be bounded in different ways. And so why we are studying the surface roughness, understanding the surface properties of pharmaceutical carriers could help us understand how the ingredient is binding. So we could improve the effectiveness of the drug delivery processes. Today, I'd like to show you the direct measurement of the specific particle surface, which could help understanding the binding mechanism. I'd like to introduce the particles we're going to study. So we have here SEM and TEM image of clusters, mechanically durable and hollow clusters. As we can see in TEM, they are quite porous. And the porosity is there in order to prevent the ingredient from recrystallization. So key aspects and interest, we are interested in particle texture, or how it looks like, and what is the difference in surface roughness between particles without the ingredient on top and with ingredient. So first of all, we're gonna find a representative particle. Then we're gonna navigate there, measure the surface roughness of the representative particle, and or measure the topography and measure the roughness. So I showed you a complete workflow procedure for a quick analysis, and let's have a look at the data. So we measured a silica particle without the active ingredient. We see an SEM overview of particle. On top of it is an AFM probe. And we see the signals from SEM and AFM, and then 3D view of AFM topography. We can clearly see the black parts are the pores. And we are sure they are pores because it's in these images, it's lower, it's dark, so it's down. And then we measured silica particles with active ingredient. So it was a bit harder to find localize the active ingredient. So because it's almost transparent in SEM, but we found it and we measured the topography of the surface. So we can clearly see a huge like flatter part, which is the active ingredient. But what we are not sure where the active ingredient is, if it's only here or it's somewhere else as well. So for the comparison, we first improved the shape of or corrected the shape of the particles. So we flattened the surfaces and then measured the roughness. So we found out on silica particles without active ingredient, the roughness is approximately 123 nanometers. In case of silica particles with active ingredient, it's quite different, depends where we are. But what we can see that the roughness, even on parts where we at the beginning thought that there is nothing, there are pores, we found out that the roughness is higher. So it means what happened is that we filled the active ingredient, the active ingredient was bound in the pores, but also grew above it. So, and created some clusters. It's also visible over here. So it seems that active ingredient is in the pores, but as well on top of the pharmaceutical carriers. So if I summarize, we showed an AFM-in-SEM tool, LiteScope, for direct analysis of the surface texture and roughness determination. We found out that the active ingredient is in the pores and somewhere also on top of whole carrier. And we found out that the surface roughness of particles with active ingredient is higher. Also probably because of created clusters of API instead of just getting it. Because first of all, we thought that the roughness will be smaller as the pores will be filled and it's going to be smoother, but it's not completely true, or at least not in these samples. So observing the changes in particle roughness and observing direct changes can explain how API, active ingredient, is bound on the carrier, and thereby, if we understand the process of binding, we can improve the drug delivery technology. Let's get to the other use case, and let's have a look at the role of powder surface roughness in ceramics. Ceramic engineering is focused on, or what it does from the research part of view, ceramics is created from inorganic non-metallic materials, which are either crystalline or partially crystalline structure. And in order to get the material, the whole ceramic compound, we need to start from the powder, prepare the material, and understand the surface properties surface roughness could help us to understand the structure of ceramic compound. And if we understand surface properties in micro nano range, we can understand the bulk properties, because bulk properties of whole ceramic device or compound. And so this surface of ceramic powders affects the sintering process, or the properties such as flowability, or how the particle is compact, and other properties and functionalities. We cooperate with Professor Matza from SATEC BUT, and he said a nice quote that LiteScope pioneers direct analysis of ceramic powder roughness, and as they've never, or he doesn't know about anyone who does research like this, he tries to reveal correlations with macroscopic properties on these materials. So what is the material? We're going to have a look at zirconia powder particles. They are partially stabilized zirconia ceramic powders. They have superior mechanical properties such as high strength and flexibility, or heat insulator properties, and so on. And they could be used in telecommunication, environmental, or dental products. And so what we're going to focus on today is what is the roughness of initial powder, and what is the roughness after calcination process. So what the calcination actually does to the surface of the powder particles. So as I said, we're going to have two types of the powder, before and after calcination process. If we have a look from overview, they look pretty much the same. There are different sizes of particles, and but they look a lot different when we have a closer look. So we have raw powder over here, it looks quite smooth, and calcinated powder over here. And what is the calcination process? It's a process of strong heat below the melting point, which evaporates the volatile components. So in this case, as the sintering temperature is over 1,000 degrees, the calcination process was done at approximately 600 Celsius. And so already in SEM, we see that there are differences, but we're not sure how much of the difference it is. So let's have a look at the topography measurement. This is a 3D AFM view already after the shape correction. And we calculated the roughness to approximately in RMS 130 nanometers. This is a raw powder. In case of calcinated zirconia powder, it's approximately 110, so it's quite similar to the previous powder. But more importantly, if we have a look at height profile, we see that the surface looks different. Even though the roughness is similar, the developed interfacial area ratio is 10% higher in calcinated powder. So it's quite a change. But what it means that the surface roughness has the same, like, bigger peaks, but there are smaller peaks on top of it. So basically, it means that the calcinated powder has much larger surface area per the same distance. And what it causes, most probably, the powder is less compact and has higher flowability, which we knew from previous experiments. So This is probably the reason. So what we found out, that the surface roughness of both types of powder are quite similar, but the developed interfacial area is different, higher by almost 10%. So it corresponds with the higher flowability of the powder. So microscopical properties are linked to macroscopical properties. So this kind of research, observing the changes in the particle surface at nanoscale, can cause can improve fabrication technology of ceramic components with more suitable macroscopic properties such as moldability, durability, whatever is needed for the specific application. So right now I showed you a package for which we prepared for powders and particles. We went through a workflow which is transparent and effective, as we can choose a specific representative particle, measure on the particle, and continuously control the experiment. We have a built-in software in our NanoView, so the life is easier that we can calculate the surface roughness directly in this software. We can compensate the particle shape, which is always needed when the particles are small enough and it's not the flat surface, because it otherwise the roughnesses are completely different. We implemented various area selection boxes such as square, ellipse, or circular. We implemented surface roughness calculation toolbox, and the data are easily exported either in text document or a PNG. So we offer a unique commercial solution for direct measurement and calculation of the surface roughness of powders and particles, all within the NanoView software. So at this time, let's have a look at two-dimensional materials. We see a recording of the graphene flake, with most probably initiation of the second this is a monolayer, so second layer over here, and we see the tip under the tilt. So here is the very end of the tip, scanning over the sample. Two-dimensional materials, well, they are quite a hot topic all over a few years already. So they are single-layered materials of different chemical composition, such as molybdenum disulfide, graphene, HBN, and so on. They are studied to be used in automotive, semiconductor, or aircraft engineering, and so on, because they have quite unique properties. And so if we understand the properties better, the development of new technologies is possible. But for that, we need a complex analysis to understand the microstructure defects, how they behave under different environments, and so on. And also we need to know the fabrication process, which is not usually easy for the two-dimensional materials to have it reproducible. What two-dimensional materials need? So they need a repeatable localization and analysis of one specific flake. So we have here an SEM overview of a flat surface, silicon surface, on top of it with flakes. But that's actually exactly how it usually looks like. There are so many flakes and they look quite similar, but they are not the same. And we need to know that we are measuring from at the same spot. And in order to understand the properties, we need to correlate the data together and see if we can find something which is connecting. The third, minimizing the number of sample transfers, is quite important as well, at least for the time efficiency of finding the same flake or contamination. And finally, when we have measured many or multiple channels, it's necessary to combine and correlate all the signals and post-process them. So we need, this way we get a complex characterization of the material properties. AFM-in-SEM allows us analysis of AFM and SEM signals, modalities, enabling complex surface characterization under in situ vacuum conditions. So we offer 16 measurement modalities, and SEM has many of them as well. So there is an example of 2D flake measured by several techniques. And this is one of the options how it can look like when we measure complexly. So we worked hard to get the optimized approach for complex surface analysis nanoscale. We'd like to present it on a case study of molybdenum disulfide. And we'd like to have a look at on the impact of CVD growth conditions. So from the measurement workflow, what we're gonna do, first of all, we select the flake and we do multiple measurements which are needed. Then we need to merge the layers, and then we need to correlate the data together and post-process. It looks quite easy here, but let's have a look how it looks like in reality. So thankfully, the measurement, the start of measurement is quite easy. We just turn on the microscope and automatically sweep the probe. Afterwards, we get to the contact and we can start the measurement. So on 3 clicks, we can get the image. So it's quite easy to exchange the probe and measure different properties. Then when we need to measure several times with different probes, we need to merge the layers together. So we have a merging layer functionality, which we can get the data to connect the data together and save the file. Afterwards, we correlated the data by function cpem+. Usually, first of all, if we have any incorrections in the data, we correct it by using artificial intelligence, by topography, and then we correlate the AFM signals with SEM signals or other signals which are there and obtain a correlated image. Let's have a look at the use case. Molybdenum disulfide is a flexible material with direct band gap. It has unique electric and mechanical properties. That is why monolayer could be suitable as a 2D semiconductor in advanced electronic devices. But we need to, what is known or unknown is how to reproducibly fabricate, or what should be the fabrication conditions in order to grow the monolayer reproducibly with the reliable properties we need. We cooperate with Professor Sofer from University of Chemistry and Technology in Prague. And we try to understand the properties of the monolayers which he is growing. In this case, we're gonna have a look at the molybdenum disulfide flake grown by CVD under different conditions. It's on a thick layer of silica on silicon substrate. Key aspects and interest are: what is the height, mechanical, and electrical properties of molybdenum disulfide flakes? And if we can observe differences due to diverse fabrication conditions. This is the beginning of a more in-depth research. So I'd like to show you only what are the possibilities, and most probably if you are working in two-dimensional material sector, you can think of where to use it. We'll be interested in knowing, so if you have an idea, you can write us and so on. We'll be happy to discuss it. So first of all, we localized by SEM and measured the flakes. So we can see very high material contrast of the flake and of some impurities on the surface. We see a bit of morphology, but not very much, especially not in that direction. If we measure it by AFM topography, we can measure the height of the flakes, height of impurities, and we can see that the surface is much more contaminated than it looks like in SEM. We can measure sub-nanometer thickness of the flakes, so we can see that it's half of the nanometer. But the impurities are 12 and more nanometers high. At the same time, we can measure surface charge distribution or test electrical properties of the flake, or mechanical properties using phase imaging. It's visible that the flakes are harder than the substrate. But what we don't see almost here is that we can also detect edges of additional layers. It's better visible over here on the second sample, where we did the exactly same analysis. I'd like to point out that we measure all of these channels were measured at the same time with one single probe in a single measurement. So it's one of the other advantages of LiteScope. But if we have a closer look at phase imaging, we can see it's visible here, the edges of molybdenum disulfide layers. We made it bigger to see. And what's interesting is that the fabrication conditions were on each sample different. And we can see that most probably the growth conditions caused that the layer grew differently in a, let's say, triangular shape. Here are small triangles, and it seems like we have different growing conditions, different ways of creating such clusters and not from center. So what I showed that we offer an optimized workflow and solution by using AFM-in-SEM with LiteScope, providing us multimodal analysis of two-dimensional materials. It enables us to characterize mechanical, electrical, magnetic properties together with capabilities of SEM, such as secondary electrons, backscattered electrons, or EDS analysis for chemical composition, and connecting the different information about the same place. So we had a look and discussed the optimized workflow. So we can repeatably localize the region of interest, measure complexly different material, different properties. And it's quite time efficient as it's all in one solution. I showed a straightforward signal correlation and correction that we are able in the same software merge layers from multiple measurements, select box, new area selection box is polygonal, or correct the surface shape by 3-point fit, which can be beneficial if we have some different structures in the same area. So it can help us to easily obtain and correlate the various data and better understand the complexity of material properties and later on bulk properties or other devices which are created from it. So let me summarize. We talked about, we introduced the AFM-in-SEM solution with LiteScope, as the main benefits are in situ characterization, correlative multimodal microscopy, and precise localization to the region of interest. And we introduced and optimized solutions, which we created for surface roughness of powders and particles and complex analysis of 2D materials with modes such as phase imaging, conductive AFM, MFM, or EDX. And we presented this solution on different use cases from different fields. And if I summarize, so you can imagine it, we use SEM as a controlled environment, and we can use all the functionalities which are added to your SEM. So if you have any question or idea where you could use the LiteScope, please reach us. We are happy to discuss your needs and challenges in your research. We have a wide distribution network, so you can contact our distributor as well, or you can see more on our webpage, on social media, or contact us directly. We also are gonna be on several conferences. We start at MMC next week, and we are in France, at M&M in the US, in Germany, Korea, and Prague. So I'll be happy to discuss with you at the booth and so on. So come by. So at this point, I'd like to answer a few questions which I have here, which you asked. So let's get to the first one. How small particles can you measure this way? We can detect particles from tens of nanometers to several microns, but the roughness measurement can be lost if we measure approximately 40 nanometers. But with the shape corrections, you can get many of the artifacts away from it. From the second question, which roughness parameters does the software calculate? For now, we have two parameters there. It's arithmetic average of profile height deviations, and root mean square average of profile heights. But it is quite easy to add other parameters there, and that's actually what we're gonna work on later on as well. And the third question which we have, which I'd like to answer aloud, is can we somehow access raw data after using fit and leveling functions? Actually, even though we use the fit, it's not saved in the raw data. The raw data are never lost. We don't want to change them, because if we make the wrong correction, we want to get back to the raw data. So don't worry, we have the raw data saved in the software in the file. So thank you for nice questions. And with this, if you have any other question, we're gonna stay in the chat with my colleagues. So ask or write us at the application@nanovision.com. We will be happy to discuss your questions. So thank you for your attention. Bye.